Thank you, Mike. Today I'm here to talk about accelerating deep learning and machine learning with Intel libraries. Deep learning and machine learning are hot topics in recent days and it's been used in many applications such as computer vision, speech recognition. Thanks to the advancement of computing hardware and the availability of big data, deep learning on machines became possible. Over the past few decades, Intel has been making powerful processors that provide exponential growth of computing power with more cores, more threads, and wider vectors. The processors spans from endpoint edge device to data center. Along with the advancement of computing hardware, many open source frameworks, libraries are developed to facilitate the research and development of machine learning applications. However, most those open source frameworks and libraries are not well optimized, especially they're not taking advantage of newer Intel-based systems. Some of those frameworks can be difficult to configure and use, and it's a challenge for those open source frameworks or libraries to support heterogeneous hardware from the training in data center to deployment on the endpoint systems. To address the machine learning software challenge, Intel strives to provide the foundation for success in artificial intelligence. Intel's strategy is to provide support for full stack in the machine learning applications. From the bottom, Intel makes powerful hardware processors spans from endpoint device to a data center, including hardware accelerators like FPGA. Above that, Intel provides libraries to extract the maximum performance from underlying hardware. Those libraries provide optimized building blocks for machine learning on Intel architectures. So in this diagram, we have shown the Intel math kernel libraries, data analytics acceleration library, and the Intel Python distribution for Python. Above that, we have commonly used machine learning frameworks such as Caffe, Theano, etc. Intel strives to provide optimized frameworks for some of those. So some of those frameworks like Caffe, Theano, Intel has optimized the frameworks and put it at the GitHub. And for some others, that's still in working progress. Above that, Intel provides tools, platforms to accelerate deployment. We have TAP, Trusted Analytics Platform, and we offer a new tool, Deep Learning Sdk, to facilitate the training and the deployment. And at the top, we are working with a broad set of partners to accelerate the development of specific solutions. So today I'm not going to cover all of this. I'm going to cover Intel Math Kernel Libraries, or MKL, and then I'm going to talk about the Data Analytics Acceleration Library and the Deep Learning SDK. So I'll give a quick overview of Math Kernel Libraries, and we'll introduce the newly added domain in Mkl 2017, which is the Deep Neural Networks Primitive, or DNN primitives. And then I will introduce Data Analytics Acceleration Library, or DAO, and I will show a simple example, handwritten digit recognition, as an example to show how to use DAO in a typical machine learning application. Then I will introduce the Deep Learning SDK. So let's start with Intel Math Kernel Library, in short MKL. So what can MKL offer? Performance, performance, performance. Intel Mkl Library is a high-performance library for Intel and compatible architectures. It's used to speed math processing in science, engineering, and data processing. It supports de facto industry standard APIs. So MKL is basically a fundamental math library that can be used in almost any application that requires math computation. The MKL functions can automatically scale from core to multi-core, many-core, and clusters. Those functions in MKL or primitives can extract maximum performance by taking advantage of wider vector size and multi-threads in multi-cores, in many cores, and in clusters. Here, I show some performance data using MKL. So here we compare the performance of DGEM between MKL and Atlas. DGEM is the double-digit general matrix operation. Atlas is automatically tuned linear algebra software. So we compare the performance between MKL and Atlas at core processor, and that's shown on the left, and Xeon processor that's on the right. So in these figures, for example, you look at the left side on the core processor, those blue lines represent the performance of the DGEM in MKL, and those green lines are the performance using Atlas. The x-axis is the matrix size, and the y is the performance using gigaflops. As can see, DGEM in MKL outperforms the DGEM at Atlas by 2 to 3 times. So it's very powerful primitives for a lot of math computation. We have the similar performance as shown on the right in Xeon processor. So those performances are done with Intel Mkl 11.3. Here's the performance with the same function using Mkl 2017 on both Xeon processor and Xeon Phi processor. Same thing as previous figure. The x-axis is the matrix size, and the y is the performance in gigaflops. As can see, DGEM performance. So these I forgot to mention the previous. So that was done for various threads. So here on the left figure, showing the performance for single thread, 22 threads, and 44 threads. So this figure shows that the DGEM performance scales well along with the number of threads. We have similar story for the DGEM performance on Xeon Phi on the right. So here are the components that's included in Intel Mkl 2017. We have linear algebra in the package that includes support for a lot of the functions for in linear algebra. We support sparse and dense multiplication operation for both multi-core and clusters. The BLAS and LA pack that functions mostly using linear algebra. So those functions libraries provide optimized vector-to-vector, vector matrix, matrix operations for single and double precision in real and complex types. In the FFT transform domain, the functions in Mkl package support a variety of FFTs for single and double precision, for one-dimension and multi-dimensional FFTs. In the vector math, we have functions for trigonometrics, exponential, log, etc. And they also include random number generators, which can generate continuous or discrete random numbers for the most popular probability distribution. In the summary statistics domain, we have functions to calculate variation coefficients, calculate those commonly used order statistics, min-max, variance, and covariance. And Mkl also include functions to do interpolation and fast Poisson solver. What's new in Mkl 2017 is it added a new domain, which is Deep Learning Neural Networks, or DNN primitives. So DNN primitives is a collection of performance primitives for deep learning applications. Those primitives or those functions are optimized for Intel architectures. Those primitives are optimized building blocks to accelerate the compute-intensive computation in the deep learning application. So for those commonly used deep learning frameworks, Intel strives to provide optimized frameworks. So some of those frameworks utilize the new DNN primitives that Intel has put it at GitHub that are optimized, such as the Intel optimized Caffe, Intel optimized Theano, and for some others like Google TensorFlow, that's work in progress. In addition to those DNN, Deep Neural Networks primitives, Intel also provides open-sourced library called Mkl DNN. The Mkl DNN is used as a playground for experiments, innovation, and collaboration with our partners. So for some new algorithms, we call collaboration to put it in this Mkl DNN open-sourced library. And once the new algorithms or functions are stabilized, they will eventually be added to Intel Mkl main package. Here's what the DNN domain contains. It includes a bunch of algorithms or functions that are commonly used in the most popular deep learning frameworks. So it includes such as the ReLU activation, batch local response normalization. For the pooling, the DNN primitives includes max, min, average, and also include functions for convolution, inner product, and data management, data manipulation. So those functions or primitives are commonly used in the popular deep learning frameworks for the most popular neural network topologies such as AlexNet, VGG, GoogleNet, ResNet. So here I'm going to show you the DNN performance. So this performance is to show the optimized performance on Caffe framework using the DNN primitives for both training and inference or scoring. The training performance is showing on the left, and the right is the inference. The gray bars in the chart is the out-of-box original cafe frameworks on AlexNet be used as a baseline. And the bar next to the gray bar, that's the performance improvement using Intel Mkl 11.3, which is an older version than the Mkl 2017. As you can see, there's a big performance improvement using the Mkl 11.3. And then on top of that, the bar that next to it, we got additional 2 times performance improvement using the latest Mkl 2017, which included the DNN primitives. So as you can see, with the DNN primitives, we can achieve almost 11 times speed up over the original cafe networks over AlexNet. Even better, on the latest and greatest Xeon Phi processor, that's the 2nd generation of the Xeon Phi, we got additional 2 times performance speed up using the DNN primitives. Similar story is shown for the inference on the left, on the right. Now I'm going to introduce the Intel Data Analytics Acceleration Library. So I just showed some performance data for MKL, for the DNN primitives. So Mkl library is more fundamental. It includes those primitives for a commonly used math operation. Now I'm going to talk about the Data Analytics Acceleration Library, which is another performance library that's specifically for data analytics. The Data Analytics Acceleration Library, or in short, DAO, covers all the stages of data analytics from pre-processing, transformation, analysis, modeling, validation to decision making. For each stage of processing, DAO includes the most commonly used algorithms that are optimized on Intel architectures. So DAO library provides optimized building blocks for all stages in data analytics. So how does DAO fit in the era of big data? Big data means huge volume, fast-changing data coming from various sources. We're trying to find patterns, trying to extract information, or getting values from the data to help us reducing cost, making decision, or making prediction. To get value from big data, we need a powerful engine to get the massive data quickly, and we hope the engine is able to do computation-intensive calculation from data and provide optimized performance from underlying hardware. So this diagram shows a simplified big data processing. On top, it shows the big data application such as data mining, recommendation engine, and BI analytics. On the left-hand side, those gray box, that's the data sources, such as data coming from finance, social media, marketing, manufacturing. In the middle, there's a big gray box. It loosely represents big data frameworks, such as the Spark Hadoop. So currently, those big data analytics frameworks, they run on the state-of-the-art hardware already, but most of frameworks or libraries use a third-party math library so it does not provide optimized or high performance for underlying hardware. Here's an example. Spark MLlib is a machine learning library widely used on big data frameworks. So Spark MLlib, it utilized the Breeze, utilized those linear algebra package in Breeze. With Breeze is implemented in Scala. And Breeze depends on netlib Java, which is a Java wrapper around netlib BLAS. netlib BLAS is implemented in Fortran. As can see, that from the data source to the final execution engine, there are many layers of dependencies, and you can imagine that can only provide limited performance and with only low ROI on hardware investment. So we want a solution that can run on state-of-the-art hardware. I want this solution to be a single library without so many dependencies, that this single library can cover all the stages of data analytics and provide optimized performance for underlying hardware, which in turn will provide a high ROI on hardware investment. So here comes the Data Analytics Acceleration Library. So this data library, DAO library, it covers all the stages and provide best performance, optimized performance on Intel architectures. It has all those building blocks can help you build end-to-end data applications. And the DAO support 3 programming APIs, C++, Java, and Python. As a performance library, now I'm going to show you some performance data. So we compare the k-means algorithm in DAO with that in Spark MLlib. So in this chart, we show the performance for different data size. And the y-axis is the speed up. As you can see, using k-means in DAO, we can achieve from 4 to 7 times speed up over the same algorithm in MLlib. Here are the components inside DAO. We have 3 big components. Data management. The first, data management, it includes, basically it's interfaces for data representation and access. It includes a bunch utilities or functions or connectors to help loading data from various sources in different data format, such as HDFS, SQL, CSV, KDB+, and even support user-defined data format. The data in DAO is in memory is represented as numeric table. Numeric table is the in-memory data representation. In this big data management component, it also includes functions that do compression, decompression. It includes those functions, commonly used compression functions like zlib, LZO, RLE. It also, in this component, it includes utilities for serialization, deserialization, so you can port data from or to memory. The second big component in DAO is the data processing algorithms. That includes those optimized algorithms for data analytics, which I'll cover a bit later. The third component is data modeling, which basically you can create the data structure for model, do the training, and includes functions or operations to do prediction using the trained model. Here are the set of algorithms that are included in DAO. So this list will keep on expanding. So now in DAO it includes those functions for calculating the statistics. It has low-order moments functions such as min, max, and they also include functions for statistical relationships, variance, covariance, and functions for a matrix computation. And it has included commonly used algorithms in machine learning such as SVM, support vector machine, PCA, principal component analysis, so just name a few. In DAO 2017, it added the support for deep learning. So in DAO, it also has neural network APIs. So what's different from in DAO neural network APIs from the DNN primitives in Mkl is, so the DNN primitives in Mkl provide the primitives or functions that are commonly used in the most popular deep learning frameworks. Here in DAO, the neural network APIs will provide a bit higher level components, so that allows the developers to build their own deep learning frameworks or the next generation of deep learning frameworks. So these neural network APIs is at the higher level. Oh, sorry. So all the algorithms in DAO support batch processing. Some algorithms also support distributed and online processing modes. So here's what it means. The three processing modes. The batch processing mode is the simplest case where data can fit into memory all at once. Online processing means that the data cannot be fit into the memory all at once, or it may be because the data is not available all at once. So data is fit into the computing engine piece by piece. The distributed processing just works like in a cluster, that we have a master node and several different local nodes. So data are only available to each local node, and each local node can calculate the partial result. And when all the local nodes finish calculating the partial nodes, those partial results will be merged and get a final result. So that's the three processing modes that are supported in DAO. Those are the key features in the new DAO 2017. As mentioned earlier, so in this new library, we added the neural network APIs to allow developers using those optimized building blocks to construct their own deep learning frameworks. And we add the Python API support in DAO 2017. So you can easily install the PyDAO through the Anaconda package by invoking conda install, or you can get the Python API or PyDAO from Intel distribution for Python. And Intel has added the open source project on GitHub for open source DAO. Now I'm going to show you a simple machine learning application, a handwritten digit recognition, as example of how to use DAO in the machine learning application. So here's the little demo window. We have a doodle frame, and there are two white boxes. On the left, the big white box, you can write any number from 0 to 9. And after that, you click Go. And on the right little white box, it will show the value or show the digit that's been written on the left. So it's a simple one-digit recognition, and once you click clear, you can write another digit. Let me try a few. So that's just for fun. Maybe you can try a little. Oh, sorry. So that's okay. Here's another one. Okay, so you get the idea of the handwritten digit recognition application. So the handwritten digit recognition, it's basically the prediction stage or the inference stage or scoring stage in a typical machine learning pipeline. So where does the model come from? In this application, so we use the publicly available pre-processed training data that's available at UCI website. The model is obtained by training those training data. In this example, we use the multi-class SVM support vector machine for 10-digit recognition. In the same website, it also provides almost 18,000 test data. Using the SVM algorithm in DAO, we achieved 99.6 accuracy. And what's convenient in DAO is it also provide the utilities, like provide functions that you can print out those performance metrics. So here we print out the confusion matrix, we have average accuracy and F-score, etc. Now I'm going to show you the C++ code snippet for how to use DAO in a typical machine learning application. So for the training, here's the code. As mentioned earlier, the data in DAO is represented in memory is called a numeric table. So we need to load the training data into memory and store it as a numeric table. So the first thing is create a numeric table. So here we defined a class train data source, which is a CSV feature manager that's going to load data from CSV file. Once we have defined this object, we want to load the data from the CSV file. So we call the function load data block. So that way, the training data are loaded from the CSV file into memory. After that, we create an algorithm object. In this application, we use the multi-class SVM algorithm. So we create an algorithm, and then we set input for this object. So input for the algorithm is the training data which we just defined and loaded. It's called the train data source. Then we can build the multi-class SVM model by calling function compute. After that, we'll get the results. The results contain the trained model from the training data. So what's neat in DAO is DAO provides utilities to help you serialize the learned model into a file. So in this case, we are creating a model file called model, and we serialize the trained model into a file so that this file can be ported to a different system for different application. So here I show you the major steps in training, how it works, what does it look like in DAO. Now it's the prediction. So similarly, we defined a test data source, which is still the same. It's a CSV feature manager. We load the data into memory by calling load data block, and we still use the SVM algorithm. So now the input to this algorithm is the model, a trained model that we just did. So in DAO, it has utility to read the model from a file to deserialize the learned model. So after you feed in the model and the test data, you do same, you do compute so that you get the result. And the result is the digit that's being tested. So this is the prediction stage or scoring stage in machine learning. So here in the handwritten digit. Here's the performance comparison between SVM in DAO and scikit-learn. Scikit-learn is another popular Python library for machine learning. For this specific SVM performance, we compare the performance in both training and the prediction. As can see, that DAO SVM outperforms the scikit-learn algorithm. For training, we have more than 6 times speed up, and for prediction, we have more than 11 times speed up. Now I have introduced Intel Mkl and Intel DAO. Both libraries provide optimized building blocks for machine learning, and they provide complementary solutions for big data application. So Intel Mkl is more at a lower level. It provides primitives for most commonly used math computation. It supports C and Fortran. Intel DAO is a little bit higher level. It includes more algorithm specific for data analytics, and it supports Python, Java, and C++. Now I'm going to introduce the new tool, Intel Deep Learning SDK. As mentioned at the beginning, Intel supports that's the Intel strategy to support a full stack of software application. At the very bottom, I just introduced the Mkl Library and DAO library, which extract maximum performance from underlying Intel platforms. And on top of that, using the DNN primitives in Mkl, Intel provide optimized frameworks such as Intel Optimus Cafe for single-node and multi-node CPUs. So on top, Intel provides another tool, a deep learning SDK tool, to accelerate design, training, and deployment. So Mkl and DAO are more of developer tools who cares about performance. And the Deep Learning SDK is more of an end-user tool for quick installation, training, and deployment. So here's what the Deep Learning SDK look like. Here are a couple screenshots of the tool. Deep Learning SDK, it includes 2 tools. So one tool set for training and another tool set for deployment. So using the Deep Learning SDK for training, it can simplify your installation, and you can select those Intel optimized deep learning frameworks by using this tool. You can automatically install those optimized frameworks. And it provides easy and visual way to set up the training data. And you can use it to tune and run the model with automatically tuned hyperparameters, since underneath the Deep Learning SDK, we're using the Mkl and DAO to extract maximum performance. And this deep learning tool can visualize the training performance and the accuracy. The deployment tool can help you to import those trained model regardless of the training hardware. So you can port the trained model using this tool from CPUs or GPUs. And this tool can help you compress the data model size for targeting hardware. For example, if you're using the edge device, you want a minimized size of a trained model. So this tool can help you to improve the execution storage through model compression and weight quantization. So that's a tool can help you to build, to port your model. The Deep Learning SDK can accelerate your deep learning solution by using simply you plug and train or plug and deploy by simplify your installation for deep learning models. And this tool can help you get maximum performance, since underlying those tools use the optimized building blocks. With this tool, it can help you increase your productivity. It can shorten your time to market for training and inference. So here's the summary. Intel Mkl and Intel DAO are both libraries, performance libraries, that can provide high performance, and it can provide you optimized building blocks for data analytics and machine learning algorithms on Intel CPUs. The DNN primitives in Mkl can speed up the intensive computation in the commonly used deep learning frameworks. And the neural network API in DAO will allow you to build your own or the next generation of machine learning frameworks. Mkl and DAO are more for application developers who want to improve performance. And then I introduced the new tool, Deep Learning SDK, which offers tools to facilitate, develop, train, and deploy deep learning solutions. So deep learning tools is for end user who cares for productivity. Then here are some resources for what I mentioned earlier. If you want to know more about Intel machine learning strategy, you can find those at software.intel.com. On this website, it also includes a bunch of tutorials, videos, webinars for machine learning strategy at Intel. So Mkl, you can get Mkl from Intel Parallel Studio or Intel System Studio, and the link gives you the support where you can get all the information about Mkl. For DAO, you can get a DAO as a standalone library or you can get Dell from Parallel Studio. And Dell also has an open source version at GitHub. For all those libraries, Intel provides a free community license where you can download those libraries for free, and it's free to distribute, to use those libraries and distribute your application using the libraries. And the last link provides the place where that's the Intel optimized cafe using the DNN primitives in MKL. So with that, thank you very much.